Okay, here we're going to show kind of how that ideal gas model and show when it's applicable and when it isn't. Okay, and to do this, we're going to use water at 700 degrees Fahrenheit at two different pressures and determine if either of those act as an ideal gas. So the way we're going to do that is we're going to use that compressibility chart that we've dealt with in the past. Okay, and then for that we need our relative temperature, which you'll remember is my temperature divided by my critical temperature. I will also need my relative pressures. So I have 1 and I have PR2, right? And this is going to basically be P1 over the critical pressure and P2 over the critical pressure, right? So the 1600 and the 160, okay? So I need to go and I need to find we'll start with the temperature. I need to find my critical temperature and critical pressure, okay? So I go into my chart here, right? These are it gives me the molecular weights, which I don't need, but I do need my critical temperature and critical pressure for water, which is 1165 and 218. So that's in Rankine. This one's in atmospheres, so we'll have to do some conversions to go around these. Okay, so starting with temperature, my current temperature is 700 degrees Fahrenheit, so I need to convert that to Rankine by adding 460 to it, then dividing that by the critical temperature in Rankine, which is 1165, which gives me a reduced temperature of 0.996. Now for my pressures, okay, I will start with P1, which is in PSI. So that'll be 1600, and then I'll take that times that critical pressure, which was 218. That is in atmospheres, so I need to multiply that times 14.7 psi to get it into psi. That gives me a reduced pressure of 0.499. And do the same thing for 160. 218 times 14.7. That's going to be 0.0499. Okay? So now, from these, I'm going to determine Z1 and Z2. Right? I'm going to find that compressibility factor for each of these pressures at the temperature, the reduced temperature of 0.996. So I go to my chart here, and my constant temperature lines again go this way. Okay? So I'm going to start with 0.996, which is essentially 1. It's pretty darn close enough for what we're trying to do here. So TR of 1. And my pressure is 0.5, which is, again, down here, 0.5. Okay, so I follow this line for 1 until I get to 0.5, which is right about here, maybe just a little bit below because I'm at 0.996. Okay, but essentially I'm at 0.81, give or take. Okay, as I slide over, and I see my Z is 0.81. So Z1 is 0.81. Z2, this is at a pressure of 0.05, which is all the way over here for a reduced pressure. I follow that up, and all these lines, this is where it starts converging. I don't know, I'm right about here, just shy, like a point, we'll call it 0.98 or something like that. Okay, so you'll remember our definition for an ideal gas, okay, is Z approaches 1, where PV equals RT. So this guy is ideal because it's almost 1. This guy is not ideal. What do I get from that? Well, at very high pressures, I can't make this assumption that it's an ideal gas. Again, we're dealing with water vapor here, right? So I've got a temperature that's relatively high, although for water, it's not really all that high. Okay, at such a high pressure, I am not behaving as an ideal gas. The lower that pressure goes, the closer to ideal I get. Now, again, this is for water vapor. If I do things for air or carbon dioxide or oxygen or something like that, what happens is these critical points get much different, and at more reasonable temperatures and pressures, the thing is going to be very close to 1 and will be ideal most of the time. Okay, so again, this is just to show you that, just because it's a gas does not make it ideal. It can only be an ideal gas if it's a very high temperature or very low pressure relative to that critical point, which for things that we think of as gases, i.e. not water vapor, but things like oxygen, carbon dioxide, these are the sorts of things that will behave as an ideal gas, and moving forward will almost all the time be treated as an ideal gas.